In a previous video, I talked about digital logic gates like we see here. We've got the NOT gate or inverter, the AND gate, where you have to have both of the inputs selected, the OR gate, where you can have one or the other or both, or the exclusive OR gate, where you can have one or the other, but not both. Okay, and so the question is how can we use these digital logic gates to actually build something? And I'll come back to that in a second, but think about that. And I wanted to talk about binary addition. And adding numbers in binary works exactly the same way as it does in our regular old decimal system. And if you're not familiar with binary numbers, here's one here. And we don't do this for a decimal system usually, where we have a leading zero, but that is common in binary. But I mean, just 101 like this is still the same thing as 0101. We just keep this as a placeholder because we want, in this case, this number to be 4 bits wide. But that's just arbitrary. That's just because I decided I wanted to do it that way. And so if I have, well, maybe it's important to note that for a number like this is the ones place, 2, 4, you can see that it's kind of hard to tell that, and 8. And so in this case, this number is a 1 plus a 4, which will give us 5. So that number is 5. Now, I'm going to just pick some random other 4-bit number to add. We're going to add these two numbers together. Well, first of all, what is this number? Well, it's got a 1 plus a 2 plus an 8. So that is 11. So in decimal, I kind of lined this up badly, but I mean, we know that that's 16, right? Let's see what happens here. Well, 1 plus 1, well, that's 2, but in binary, you only have 0 and 1 to work with. So you put a 0 there and carry your 1 over, just like you would in decimal. And so we got a 1 plus a 0 plus a 1. Well, that's 2 again, so put another 0 in there. Carry the 1 again. And we got 1 plus 0, which is 2 again. And carry that one. 1 plus 0 plus 1 is 0. Well, and carry the 1, so we can just bring that down. So the result would be, well, 0, 0, 0. What is this? Well, it turns out that if we keep going this way, these are all powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So 2 to the 4 is 16. It's a little blurry. So this number right here is in fact 16. So that's how binary addition works. And notice we had to carry our ones and stuff like that the same way that we would if we got, some value above 10 here. Like if we were, I don't know, say 19 plus 2. Well, that's 11. So we put the 1 there. Carry the 1. 1 plus 1 is 2. And 19 plus 2 does in fact add up to 21. So we're doing the same thing either way here. So that's how binary addition works. So would there be a way to build a circuit that would do this? And in fact, there is, with the carries and the whole works. And if we were to build a truth table for that, it might look something like this. Now this A and B would be our two numbers up here that were, this would be A, this would be B, even just this digit and that digit. This digit's A, this digit's B. The C would be whatever carry we might have, up top here. That's what the A, B, and C are here. And look and see what happens here. So if A is 0 and B is 0 and we have no carry, the result of that is going to be a 0, and we're also not going to carry anything, and so on. And so this is what the truth table for that looks like. What's interesting about this, assume we don't have any carry for the moment. We're just doing the first, your first column here. And this is the results you would get for that. This is the exact same thing you would get from an exclusive OR gate. A and B are 0, you're going to get a 0. A is 1, or A is 0, B is 1, you're going to get a 1. The other way around, you still get a 1. But if A and B are both 1, you get a 0. That's exactly what an exclusive OR gate does. So if we analyze this truth table, what we end up getting is a circuit that looks like this. And this is a 1-bit adder. That will do the first part of this arithmetic here. And it also accounts for whether we have something that we're carrying or not. So you can see we have that A and B and maybe a carry. And just through a few logic gates, we've got a couple exclusive OR gates, a couple AND gates, and an OR gate over here that will give us whatever our sum value is here. And this carry here will give us whatever we might be carrying over here. And so if you put all that together, that pretty much gives you binary addition right there. And the best part about this is this particular circuit, well, that was just for the first column, but you can chain these together. This carry here, we could copy this whole circuit, and this carry out here will be the carry in for our next part here. And then our A and B would just be whatever's in the next column here, and so on. And so you can arbitrarily chain as many of these together as you want to, which I in fact did. And when you do that, this is a 4-bit adder. So this has, look at this monstrosity here. This has 4 of these chained together in exactly that way. The chips in there are some OR gates, AND gates, and some exclusive OR gates. And what I did here, I'll actually give this thing some power and we'll see what it does. It should do exactly what I just did on paper for binary addition. So we'll get that plugged in there. And right now, like how I did this, this would be like my first number. It's all set to zeros right now, and these 1, 2, 3, 4s are totally irrelevant now, but it follow the same places. You know, we've got the 1's place, the 2's place, the 4 place, and the 8th place. Just like we had, where did I put it? Just corresponding this way, 1, 2, 4, 8. And so all of these would be our A values. All of these would be our B values. So if I were to dial this in, this exact number, well, let's try that actually. And this might be kind of hard to do holding the camera at the same time while I do this, but I'll maybe like, let's see, see if I can do this so you can see. But if I just toggle just this guy, and this is going to be my output here. So this is my 1's place, 2, 4, 8s, and 16 would be kind of our overflow because this is only a 4-bit adder, but any carry out would be the 16th place. So right now I just got to get 1 dialed in there on my A input. If I put the same 1 value on my other input here, oops, kind of wiggly, but we can see, well, 1 plus 1 is in fact 2. And this should work for, well, any 4-bit number that we can think of to do. So I'll try putting in our example that we had on paper there. It's kind of hard to get these toggled. Okay, so 1, 0, or rather 0, 1, 0, 1. That's what we have here, right? 0, 1, 0, 1. And we can actually check that. Should give us, well, the same thing down here. 0101. That's the reason why I made this a different color, because this is just an overflow. So pretend that red one doesn't exist there, but you can see 0101. And so let's try, what did we have for a number here? 1011. So let's try plugging that in over here too and seeing what we get. 1 0 1 1. Maybe. And this is a little wiggly. There we go. And you can see what happened was the same thing we got here. All zeros for these guys, but then our 16th or our carryover here did light up. And you might not have been able to see it, but as I was toggling these different ways, it was in fact calculating whatever those values were. And you could actually check that with math on paper, but I've actually debugged this thing completely, and this does actually work. So this is how you could build a 4-bit adder. And I wanted to do it just to kind of see if I could. But what's kind of funny about that is I just got a whole big old load of chips here delivered, a whole bunch of them. And this guy right here, let's see if we can get that in here. This chip, the 74LS83, is exactly this whole 4-bit adder business right here, just right on this little chip here. So I don't need to actually use this for anything, so I'm going to actually deconstruct it, but I just kind of wanted to show it off first that I did actually do it. But there's no real sense in using this device for anything when you could just use one of those guys right there. So that's all for this one, and that's all for this thing. That's going to get recycled into some different projects.